Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So this afternoon I'm going to finish this section on transactional memory by saying a bit more about the performance of TM systems when using them to build shared memory data structures. And we call this work STM in the small, which is the title of the paper we recently had at the ڳC conference, because we're really looking at slightly different workloads for an STM system than the Labyrinth benchmark that I mentioned before lunch. So Labyrinth was using transactions with hundreds of thousands or millions of accesses within them. Whereas here, we're just looking at fairly small transactions that might be used to update a shared memory data structure. So maybe splicing an entry into a doubly linked list by updating a handful of pointers, maybe 4, 5, 6 or so. So the motivation for this work is that previously there was a range of techniques that could be used for building shared memory data structures, but neither of these really seemed ideal. So on the one hand, we could build data structures directly from the single word atomic operations that processors provide these days. So typically a single word CAS operation. And this is very difficult to use because the single word operations, as you'd expect, just let you update one location at a time. And so that means if you're doing something that involves multiple locations, like splicing a node into a doubly linked list, then you have to do the design very, very carefully to preserve some invariance about the data structure. So it might be that if there are multiple threads all trying to work on that doubly linked list, you'd need to work out exactly when an item is considered to be present in the list, when it's removed, and exactly how that property is updated as you do these individual single-word operations to change the representation of the data structure in memory. So that's fiendishly difficult to do. And I think Morris will have some examples this afternoon and later in the week illustrating some of the techniques that have been developed over the years for developing these scalable fine-grained data structures. There's a rule of thumb that a good design and evaluation of a data structure is a research paper at a good conference. So that illustrates why it's fiendishly difficult. And even once a data structure has been published in a good conference, it's quite common for there to be subtle bugs in it, either in the actual algorithm or in the way that the algorithm's been translated into pseudocode to present it. It's very, very difficult to be sure that a data structure is correct. And often the people with expertise on doing formal checks of correctness in this area are unfortunately not the same people who have expertise in building shared memory data structures. So it's often the case that there are bugs left lying around, only realized perhaps over time. Now, at the other end of the spectrum, we could use transactional memory in the way that I've been talking about earlier. This really moves us to the opposite of all of these problems. It lets us update multiple locations in memory as a single atomic transaction. And therefore, for that doubly linked list, we can just do an atomic transaction to update all 4 pointers and move the list from a consistent state where an item is missing into a new consistent state with the item present in it. I said earlier that I'm going to focus on performance here, but we can give the programmer some rules of thumb for getting decent performance. If they write a data structure where operations do not conflict unless they really need to, that's likely to lead to a good scalable implementation. So for example, on that doubly linked list, as long as we're just touching the pointers in the region near where the list is being manipulated, the system will probably scale well. If, on the other hand, every transaction maintains a count of the number of items in the list, and we increment that when we put a new item in and decrement it when we take an item out, that'll scale poorly because all of the transactions will be conflicting with one another. And then finally, using atomic transactions lets us insulate the programmer from a lot of details of the hardware. A particular problem that comes up with single-word primitives is how the processor's memory model interacts with the software. And that can appear to reorder memory instructions, even in some cases ones that seem counterintuitive, For instance, if you dereference a pointer and then dereference the value that you've just loaded from memory, some processors can actually appear that those executions occur in the opposite order, even though it looks like there's a data dependence between them. So if we've got a nice TM system and a property such as the one I described this morning, that we have strong semantics for race-free programs, then that insulates the programmer from a lot of details of the processor and a lot of the problems of making a consistent update to a data structure just one memory location at a time. But the big problem with using STM systems for building these data structures is the performance they give. So I'm not sure if this is a phrase here, but in the UK there's this phrase, the elephant in the room, which is a big obvious problem that no one is really very keen to talk about. And often with STM systems, the elephant in the room is the performance of the STM. So this graph here is looking at the same kind of benchmarks that I was talking about this morning. I've normalized it against throughput. So we're looking at, I think, the performance of a skip list with insert, delete, and lookup operations on a fairly large key space with threads picking uniformly at random in that key space which operation to do. And one here is the throughput of an optimized sequential implementation of the skip list. And the line here with the triangles is the performance of an STM system, modeled roughly on a design from Rashid Gherawi's group in EPFL a year or so back. And the performance here is comparable to the Bartok STM system I've been talking about. It's roughly half the speed when running on a single thread, so we've lost a lot of time doing extra bookkeeping. When we go to 2 threads, we've made up the ground that we've lost, so it's not as bad as some workloads would be. And then we scale a bit and get to a kind of flat level of performance by the time we're near 4 or 5 threads. So on the one hand, if we just had the triangle line here, this would look pretty decent. We've got a data structure that's much, much simpler than other concurrent data structure implementations for skip list, and it gives some degree of scaling on the kind of multi-core processors that we have today with maybe a quad-core system. But I've also included a line that shows the performance of a good scalable non-blocking linked list developed from some previous work with a PhD student, Keir Fraser. And the performance of this scalable skip list is much, much better than the STM system. If we look at the single-thread performance, the scalable version has only got about a 10 or 20% overhead against sequential, so we're not paying much for the concurrency control. And it scales almost linearly up to 8 hardware threads that we had on this machine. So if we're building shared memory data structures because we want a program to go fast, then obviously we'd prefer this version over this version. And indeed, it might be that we only get very limited scaling on relatively modest multi-core processors if we use the STM version directly. And this observation led us to revisit the question about how exactly to design an STM system and the interface to the STM, and to see if we can adapt it in order to try to get better performance and move from this STM line up to more like the single-word atomic CAS-based linked list or skip list. So we could really view this design space as containing multiple options, of course, in addition to just the STM and the fine-grained CAS-based data structure. So we've got the option of just using very simple locking, just having a single lock protect the entire skip list, acquire that to do an operation and release it afterwards. And there we have an implementation that's obviously correct if the sequential code is correct and we do the locking right. It's very fast under low contention because acquiring and releasing a well-implemented lock is going to be good on a modern machine. It's likely to scale poorly, of course, because everybody needs that same lock. And we don't have composition in the form I was describing last Thursday, where we might want to glue together multiple operations on different shared memory data structures. We have the CAS-based implementation with the properties I just described, all these difficult issues. And then we have the STM implementation, where we get benefits in terms of ease of programming, but lose out on scaling against the CAS-based implementation, and lose out in terms of low contention implementation against simple locking. So we've been trying to find new abstractions that are perhaps combining some of the good properties of these different alternatives. And the particular abstraction we've been looking at is a system we call SpecTM, which is a system that provides support for short, specialized transactions. And by short transaction, I mean maybe up to half a dozen memory accesses within the transaction. And by specialized, I mean that instead of supporting the general purpose atomic statement construct, we have an interface where the programmer is a little more explicit about the memory accesses they're making and properties that the data structure has. I'll come back in a moment to some concrete examples of what code looks like when written using SpecTM. So the example that I've used before, I'll stick with, which is a double-ended queue with left and right index pointers and then an array holding the list contents. I'm using a slightly different STM system to Bartok, though, in that here that's an example of a lazy versioned word-based STM. Now, word-based means that the concurrency control in the STM is being done on individual memory words or cache lines instead of on objects. So this is all happening in C or C++, where we don't have the same degree of control in the runtime system that we do in C# or Java to add extra header words. We want to use, for example, an unmodified memory allocator, so we can't put extra header words in straightforwardly. So what we do instead for a word-based STM is to have a hash function that maps memory addresses that the program manipulates into slots in a table of ownership records. So the address over here for the data is just a normal location in the program's heap. The hash function maps that onto a table of perhaps 1,000 or 2,000 ownership records. And each of these ownership records has the same format as that header word that we added in the Bartok STM system. So you could think of it as instead of having those header words on every single object, we keep a table of them in the heap in a dedicated region, and we use the hash function to link data to the STM metadata. Now, by lazy versioned, what I mean is that threads keep a private log of all of their writes. So instead of doing the updates directly to the heap as they run, the thread will keep a log recording the values it wants to store, and then once it's validated successfully at the end of the transaction, it'll write all those values back to the heap if there's been no conflict. So each thread's data structures for the STM look a bit like this. We've got a per-thread read log that tracks the addresses that the thread has read from and the version numbers that we saw in those ORECs from those locations. And we have a per-thread write log that tracks the addresses we've written to and the values that we're wanting to store there. Now, if we turn to look at the code that would be used in a traditional system with this word-based interface, it's something like this, probably quite similar to some of the compiler examples I had earlier, in that we've got a loop here that's running within the pop left function, attempting to make a single atomic update to the heap. We call a start transaction function at the beginning. This is C, so we're allowed to take the address of local variables, and this is taking the address of a transaction record that we've stack allocated, and that record will hold pointers to the read log and the write log that I had on the previous slide. Now, as the transaction runs, it calls these txRead and txWrite for each of the locations it accesses, and then at the end it calls txCommit, and that keeps looping until the commit manages to succeed. So this is essentially the code that we had for the performance results on the earlier slide, and the implementation we started from gave about a factor of 2 slowdown on sequential code. So we spent some time looking at where this slowdown came from, and then trying to develop techniques to address each of the different problems that we were finding. And there were 4 major costs here. The first one is the way that we were handling the transaction, the process's state at the start and the end of the transaction. The approach we took was that the start function would take a snapshot of all of the processor registers, and then if the STM detected a conflict midway through the transaction, we would restore the processor registers from that snapshot. So that makes it more straightforward to use this interface, because the saving and restoring is happening automatically. But the processor might have a whole lot of extra registers that the compiled code is not using inside the transaction. And so we're saving and restoring more state than we actually need to. Another problem is that because we're using a lazy version system, the read function needs to look at the transaction's private log in order to see earlier writes. So we don't have any earlier writes here, but nevertheless the read calls are going to be looking through that log in order to see if there's a preceding store to the same location. Now, we went to a lot of effort making those lookups as efficient as we could, So we have a filtering table that tries to map addresses in the heap to the location where in the log a store will be present if there is one. But even so, we're doing a few memory accesses in each read in addition to the actual data access and the concurrency control that we need for it. There's a bit of extra work just managing bookkeeping to do with the logs. We need to keep track of how large each of the logs is, and then we need to increment these counters when we do a read or write. And that seems like a small piece of work. It might just be a single increment instruction on the processor. But as a whole, this transaction itself is very small, and so the relative impact of doing these small bits of bookkeeping work becomes a significant fraction of the overall overheads that we're encountering. And then finally, there's the cost of the extra cache lines involved in our use of the ownership record table. Because on each of the reads that we make, we've got one read from the data location in the heap, and then after doing the hashing, we do a second read from the ownership table. So we're touching twice as many cache lines as before. And even if we don't get any problems with false sharing, then we're adding contention in the cache for space, and we're adding the extra delays as we fetch that second line in addition to the first one. So taking all these factors together, that gets us this twofold slowdown over sequential code. Now the idea with SpecTM is to provide an interface that lets us express some of the properties that the programmer knows about the data structure in a way that the STM system can then exploit in making the implementation run fast. And this is that same example of the double-ended queue, but using SpecTM for the data structure accesses. The first access here is a call to TX read-write-1. And what that function is saying is that it's going to be the first access in a transaction. And the transaction is a specialized kind of read-write transaction that's going to read from a set of locations and then store new values into all of those locations. So in this case, we're getting a number of benefits. We're avoiding the need to keep track of a counter for the read or write sets because the programmer is supplying this explicitly, saying that this is guaranteed to be the first access inside the transaction. And we're avoiding the explicit saving and restoring of all of the processor state. The transaction gets started when we call TX read-write-1, and no state has been stored. We're going to have to deal automatically with conflict detection and rollback in this example. So as I mentioned, each of the read-write calls carries an explicit sequence number. So we're doing two reads, one of the left index, and then the second of the content of the items array. We have a validity test here, so instead of transparently going back to the start, we're checking if the transaction has seen a consistent view of these two memory locations. And if not, then we go to restart just using a normal loop in the source code. And then finally, when we are ready to commit the transaction, we use a commit function that takes all of the new values to store as parameters to the commit. So in this case, we're doing a commit for a two-word read-write transaction. And this parameter here is the one to store in the first location we read, and the null just under the label there is going to be stored in the second location, so nulling out the slot in the items array. And a consequence of handling the writes in this way is that, of course, the reads don't have to look for preceding writes, because all of the writing is being delayed until the transaction is ready to commit. So we have a slight saving on the cost of the reads in this way. Now looking at the full API for short transactions in SpecTM, we have one set of functions here that are for doing single-word transactions as a single function call. So there's one function for doing a transaction that reads from just one location, another for writes, and another for a compare and swap style of transaction. And these functions here are just wrappers around the normal memory accesses with enough code to synchronize with any concurrent transaction. So if there's a bunch of transactions all running and all making updates to the heap, then if we do a read using the TX single read, we're guaranteed to see a version that's synchronized correctly with those writes. The next set of functions are the ones the previous slide illustrated, the support for read-write transactions where we have a series of functions to do first, second, and third, and so on reads, and then commit functions that take the new values we want to store. We've got abort functions for if we have got to a stage where we decide to roll back the transaction, and then the validation function which checks whether or not the transaction has experienced a conflict. We've got a few more functions as well. There's another API for dealing with multi-word transactions that are read-only, and this is exploited in the implementation to give better scaling. So we have a similar API for the first, second, and so on reads that we do in a read-only transaction. And then we have validation functions as before. And finally, if we have a transaction that reads from some locations and writes to others, these two APIs can be used in combination with each other. So a call like this one saying read-only 1, read-write 2 is saying that we've read from one location and we've made read-write accesses to two locations. And then on the right-hand side here are the new values to store in those two locations. And we also need an upgrade operation for if we start out by reading from a location and then decide later that we want to make an update to it, we'd use this upgrade to move it effectively from the read log into the write log. So the API is clearly a lot more cumbersome than programming with atomic sections. And it's a lot more cumbersome than programming with the word-based STM that I started with. But our impression is that this is still a good step above using a single word compare and swap operation, because the STM implementation is still dealing with providing atomicity. So, for example, in the skip list, when we're inserting a node, the insert handles all of the levels in the skip list as a single atomic update, whereas the original lock-free skip list, a lot of the complexity came from handling those individual inserts at different levels and making sure that a half-inserted or half-deleted node was treated correctly in the rest of the algorithm. So we've got this kind of middle ground between using single-word CAS with a lot of programmer complexity and using transactions. And we're retaining the ability to do atomicity, but we've made the programming API slightly more complex. Now we get a decent improvement in performance for the effort here. Exactly the same experiment as before with 8 cores and a workload manipulating a skip list. And the workload using short transactions is about halfway between the implementation using CAS and the implementation using the original word-based STM. So we've reduced the sequential overheads here, and we've improved the scaling a little bit on this machine. Now, if we go back to the list of problems in a typical word-based system, we tackle the first 3 of these. We avoid the costs of transparently saving and restoring the whole processor register state by making that explicit in the program and just having a normal loop for re-execution. We avoid the need for reads to look for preceding writes by buffering the writes to the commit call. And we avoid the need for the STM to manage the logs by having the programmer give these index numbers when calling functions. But we still have this cost for the additional cache lines that are touched during the transaction. And our impression is that it's that additional cost for cache lines which is leading to the worst scaling of the short transactions compared with the CAS-based skip list. So both the STM and SpecTM with short transactions have this inflection point in the middle where we scale up to about 4 and then the scaling drops off above that. So the next thing that we looked at is how to avoid the need to touch quite as many cache lines for most of these workloads. And the idea we've explored here is to move from having a hash function to associate the data with the OREC table to combining both of these together on the same cache line. So this is specializing the transaction in another way to just using that SpecTM interface. It means we can't just use the normal data structures that the program uses. We've got to rewrite these to allow the data and the metadata to be co-located. So that requires some additional work on the programmer, but as I'll show in a moment, it leads to some more opportunities for better performance. And the approach here we've taken is in C++ to define a class called a tvar, and have a tvar encapsulate the piece of data along with the metadata. So a tvar of void star will hold a void star field and then the metadata for when that is accessed in a transaction. And this is an idea we picked up from the earlier work on STM Haskell and have then applied in an imperative language setting. So the queue would look a bit like this. We've got the array of items is an array of tvar void star. So we have one piece of metadata for each slot in the array, rather than a single piece of metadata for the whole array as we would in Bartok STM. And then the left and right indexes, they're both tvar of int, holding the index along with the metadata. Now, the performance improvement of this is a good step above the performance of the basic short transaction system. We've got rid of some more of the sequential overhead, and the scaling of the system with dedicated TVARs is much closer to the scaling of the CAS-based skip list that we were starting from as this example. We then spent some time looking at if we could get further than this. So although the TVARs still require us to keep this version number, it's likely to be co-located on the same cache line. But the version number is going to be taking up some space. So perhaps if we had a big array like this, half of the space is going to have to be dedicated to the version numbers, and the actual amount of cache space it occupies in total is going to be increased. So we were trying to eliminate the need for the version number altogether and move to an even more compact representation where we can just reserve a single bit in each of the locations that the STM is allowed to update. Now, the idea here is that we have to be quite careful. We have a single machine word here, and obviously part of this needs to be used by the application for its data, and part of it reserved by the STM system for metadata. And in practice, that means we're reserving one bit at the bottom end of this word as a lock bit for use by the STM. And we're leaving the top part of the word completely free for the application programmer to use. So if that's a 64-bit machine, then the programmer's got 63 out of 64 bits left, so enough to hold a good range of integer values. And importantly, for a lot of data structures, enough to hold a pointer, because the pointer will be pointing to an aligned memory location in most systems. And so we know that the bottom few bits of the aligned addresses are 0, and whenever we read from those locations, we can mask off the bits and realign the pointer if the STM has that lock bit set. Now, the difficulty we have is how to actually maintain correctness of the transactions once we've got rid of the version number. Because if we were to implement this in a naive way, then we'd find that the system would not actually provide atomicity or isolation. So the intuition is that as the transaction runs, we're going to log the addresses that it accesses, and we're going to log the complete contents of these words, so all of the values that it loads from memory. And then when the transaction tries to commit, we're going to reread all of those locations and check that the values are still matching the ones that we saw when we first read them. So we call this technique pure value-based validation because it doesn't involve any use of version numbers. And in the basic implementation, it almost works, but not quite. So let me walk through some of the cases where it does work, and then I'll talk about what we do to extend this and get it working in all the other cases. So one case where this works is if we're reading from a location and we see the lock bit set, because the lock bit being set means there's a read-write transaction that's currently trying to commit an update to that location. And so the reader is going to wait until the lock bit is cleared again. So we detect read-write transactional conflict straightforwardly just by using the lock bit to let writers signal their presence. During validation, then we lock the locations being updated, reread, and check the values are the same. But in general, as I mentioned, this is not a sound way of doing validation. And the reason for that is there's no guarantee that when we read from the locations the second time, we're actually going to get a consistent view of all of those locations' contents. So it could be that when the transaction starts running, it reads from 3 different locations, sees the value 100, for instance, in each of these locations, and then does some other work and then tries to commit. And that at validation time, it rereads those locations and again sees the value 100 in each of them and then decides there's no conflict. But there's no guarantee that all 3 locations ever held the value 100 at the same time. It could be there were lots and lots of updates going on in the system, and perhaps just after the first read, another thread replaces the value 100 by the value 200, and then does some other updates, and just before the second read in validation, it puts the value 100 back again very briefly in that location. So the version number system would detect that conflict because it would see the version number has been incremented on each of the updates. But with a value-based system, we don't notice the conflict, and we could be unlucky to find that we happen to see matching values despite the fact there's been multiple updates. And this is an example of a more general kind of ABA problem that often comes up in building shared memory data structures. So in practice, this is not sound, but there are three special cases that we identified. And in fact, it turns out that these cover a lot of the different data structures that we want to build. And in fact, what happened was we built the version like this and then tried using it. And we were wanting that to be a kind of point for comparison with some of the other systems. And we were then surprised that it actually seemed to work at all, and then set about trying to work out why it is that it was correct for these data structures and to develop some general ideas for what properties another data structure needed to have in order for pure value-based validation to work. So one possible property is if the transaction only reads from a single location, then it's correct to validate in this way. And that's because if we just need to look at one location, then we're going to see an atomic view of that. The basic processor memory read primitive is going to give us an atomic view of that one location. So in the case of the skip list, we had that property because the transactions are inserting and deleting items in the skip list, and they're doing an update for each of the levels in the list, and they're reading a counter that says how tall the elements in the list are supposed to be. So we have one read, and everything else is a read-write that we're handling with the lock bit. So we're in this one read-only location case, and the algorithm is correct. The second case is if we have any number of read-modify-write locations. As I just mentioned, the lock bit handles these, and that'll allow a concurrent reader to detect the conflict. And then the final case, which is the more subtle one, is if we have locations that satisfy a form of non-reuse property. So the crux of the problem in that example, with a thread putting the value 101 in temporarily and then putting 100 back in, is that we were going back to an old value for a memory location without having incremented a version number. Whereas if the data structure guarantees it's not going to store the same value back into the same memory location again, then if the data structures, if that location's contents is the same, we know it's not gone through any intermediate values, there's not been any conflicting update. And it turns out there are a lot of cases when we have this non-reuse property. One case is if the item in the field is a pointer to a dynamically allocated piece of data. And if we only reuse that memory after deallocating the data and reallocating it for a new purpose, we already have to be careful about that deallocation to make sure that threads agreed that the data is not being shared any longer. And the synchronization done for that is sufficient to give us the non-reuse property we need here. And another example here is if we had something that has space in it for us to add an explicit version number. So if the programmer can't guarantee this themselves, then if they're able to pack in enough of a version number into that 64-bit field to make the values not be reused, they can increment the version number every time they commit an update. And so the programmer can provide that layer of version numbering instead of it being provided transparently by the STM system to all locations. So taking a combination of these features, it turns out these are sufficient for the skip list and hash table benchmarks that I've got in this paper. And it turns out, in fact, that sometimes we get better performance by using the SpecTM with short transactions with value-based validation. Now, the difference between these is really likely just to be down to noise in the experiments. The compiler will have done a slightly different job in register allocation and lots of low-level code generation. And so the point is really that the SpecTM system and the original data structure built with fine-grained concurrency control with compare and swap are essentially indistinguishable in performance. The scaling is the same in this workload, and if you were to zoom in on the one-thread case, there's very little overhead on either case compared with the performance on the sequential machine. So just to finish this section, I've got some other performance results. These are looking at some other data structure benchmarks on some slightly larger machines, just to illustrate how SpecTM, using these different forms of specialization, is able to scale and perform better than the other systems. This one is looking at a hash table. We're on a 4-socket AMD 4-core machine, and we're comparing the STM system and then the lock-free hash table in this case, and the lock-free hash table built using SpecTM with the single lock bit idea. And the performance is much as on the earlier slides. The STM system is scaling to about 4 or 5 threads, which I think in this case corresponds to when we've filled one of the sockets in the machine. And the other implementations scale very well while they're running in a single socket, and then they scale less well once communication is involved between the different sockets of the machine. But the two implementations here are giving essentially the same performance. Now, I don't have graphs here, but we spent some time looking at exactly which of the optimizations in SpecTM is important for performance. And it turns out that this movement from the STM to SpecTM is really the succession of lots of little changes that individually give 10 or 20% improvement. There's not really a big dominating factor here. Part of this is the low-level log management. Part of this is avoiding reads, need to look for writes. Part of it is compacting the data structure so it fits on the same number of cache lines as in the lock-free skip list. And in fact, the very close correspondence between these performance lines was something that we also spent time looking at. And really it comes down to the fact that both of these implementations are touching roughly the same number of cache lines, and they're touching them in roughly the same mode. So where one of the hash table implementations needs to write to a cache line, so does the other implementation. Where they're both reading from a cache line, they're each doing that. So although the ways in which they perform concurrency control differ, and the number of atomic memory accesses that they're performing differ, or the number of atomic compare and swaps they use differ, the number of cache lines that they touch and the ordering of cache lines is very similar. And we believe that that's what leads us to similar performance in this machine. The next set of results look at a skip list again, and they have this same trend. The lines here are effectively on top of one another if I was to add error bars onto the graph. And the comparison with STM is we're getting about a 2-fold increase over STM for both of these cases, and we're getting slightly better scaling. The final set of results are looking at a 128 hardware thread machine. And this is a machine with 8 sockets, each of which has a machine with 8 hyper-threaded cores. So each individual chip has got 16 hardware threads on it, and we've got 8 of those, so 128 hardware threads in the machine. And again, we were pleased to see that the SpecTM and the lock-free skip list both perform and scale very well on this system. The STM system scales getting slightly improved performance until we get to this 64 core point. And what happens at 64 cores is that the operating system starts scheduling our threads using both hyperthreads on the same core. And so there's contention for resources within that core, and we end up saturating some of those resources and don't get any additional performance by using the additional hyperthreads. So let me wrap up. I've been talking this afternoon about SpecTM, which is the most recent work we've been doing on STM, trying to come up with a middle ground between these different kinds of abstraction for shared memory programming. It tries to give some properties of STM, so we're retaining the ability to update multiple locations atomically, and therefore to update a data structure from one consistent state to another. And we still have this property of STM that we need to guide the programmer to write code with few conflicts if they want to get good scaling. But then as with simple locking, we've got this property that under low contention, the implementation is much more streamlined than a general purpose STM system, because all we have really left are the core features to do with concurrency control, and we've moved all of the log management from the STM system up to the application programmer's responsibility. And hopefully we got away from this position where writing a new data structure leads to a publishable result. Now, we have given up a lot of other properties of STM in developing SpecTM. So it is very much kind of going back to where we started with TM in looking just at shared memory data structures rather than these broader questions about having atomic sections with integration with other parts of the language and the runtime system. And looking purely at performance rather than these kind of language and ease of programming uses. We don't have the composability that I started out talking about with the STM Haskell work. So we don't have any notion for nesting transactions inside one another. And the fact that we have these IDs on each of the reads and the writes to signal if it's the first, second, or third, and so on, means that we need to structure the code in a way that we can have that information at the point we're calling into the STM system. So we can't glue together two transactions into a bigger one anymore, and we don't have support for retry or else here. But potentially these are all things that could be added back into the system without compromising the cost. We could have a static analysis that takes a program using atomic blocks and tries to infer whether the individual reads and writes can be assigned static numbers, and then uses SpecTM if that's correct. And although I've not used it in this example, as long as we're using version numbers, we have integration between SpecTM short transactions and the longer general purpose transaction. So it's always possible to fall back and use a general purpose transaction if there's something that's difficult to express with the SpecTM interface. So, and the final question then is how this system is going to interact with the upcoming hardware TM features. You might have seen announcements from Intel that their forthcoming processors will have support for a form of restricted transactional memory that will support small transactions accessing a few locations with reads and writes. And so I'm looking forward to having access to that hardware at some point in the future and seeing how that fits with SpecTM and whether we would use SpecTM as a software alternative to the hardware restricted TM, or whether we would use the hardware TM as an acceleration mechanism, perhaps to accelerate the commit functions in SpecTM. So let me stop there for this afternoon, a few minutes early before coffee. I'm of course very happy to talk with anyone about this for either the SpecTM work that we've been doing most recently, or any of the other work going on in the TM research community. If you have a look at my webpage, that's got a link to the pages about the TM book that I worked on some time back. And although the PDF for that isn't available online, the bibliography that we put together for the book is. And that's got references to a lot of the papers over the last 5 or 6 years that have emerged, exploring a lot of different options for hardware and software support for TM and evaluation of that in lots of different workloads. So let me stop there, and thank you very much for your attention.